Good morning and welcome back. As we start into kinetics, we've talked a lot about reaction rates and how we determine reaction rates experimentally. But today we're going to talk a little bit about how we can determine reaction rates, first from something called an elementary reaction, and then later in this unit we'll talk about how we determine reaction rates from um, reaction mechanisms. So being able to do that from an elementary reaction is our first step. And then we're going to talk about the collision theory, which helps to explain why reaction rates behave in the way that they do. So let's go ahead and jump into our PowerPoint for today. And that's going to take us here. Maybe. Okay, so first thing that we're going to talk about is this idea of an elementary reaction. So an elementary reaction is a reaction that occurs in just one step. So what that means is that the balanced chemical equation in that case, which is not always the case, is telling us exactly what is happening on a molecular or atomic level. So when we talk about reactions, there's a couple of terms we want to define. In addition to elementary reaction being one that occurs in one step, we're going to talk about the molecularity of reactions. And when we talk about the molecularity of reactions, we're talking about, is there one molecule involved in the reaction or two? If it's one particle, then we call it unimolecular. Two particles, we call it bimolecular. Three particles, we actually call it termolecular. And we continue on. It's really unusual to have a termolecular or more reaction. If you think about that, in order for that reaction to happen, you have to have three molecules collide, all with the right energy and the right orientation, and that's really unusual. So it is much more common to have one particle or two particle reactions. Okay, we have said, as we've talked about rate laws being determined experimentally, we have said that rate laws do not depend on the coefficients of the balanced chemical equation, and that is still true. However, rate laws do depend on the reactant coefficients of the balanced rate determining step. So if we have a unimolecular reaction, we're going to have a first order reaction. If we have a bimolecular reaction, then we're going to have a second order reaction. So those rate laws that we determine experimentally do come from those balanced chemical equations, but only for the rate determining steps. So the rate equation for any individual step is defined by the stoichiometry of that particular step. What that means, coming back to the idea of the elementary reaction, is that in an elementary reaction, those reaction coefficients do tell you the rate law, because that balanced equation is telling you exactly what is happening on a molecular level. So we'll use this later on when we talk about reaction mechanisms. Today we're going to stick with just elementary reactions. So if we know that we have an elementary reaction, our question tells us it's elementary, or our question tells us that it happens in just one step, then we know we have an elementary reaction. And so we can write a rate law from the coefficients in the equation. And so for this particular rate law, where we have nitrogen dioxide combining with carbon monoxide to form nitrogen monoxide and carbon dioxide, our rate is going to be equal to K, our coefficient, times the concentration of the nitrogen dioxide times the concentration of the carbon monoxide. Simple and straightforward. We don't need experimental data. Now, where this came from is experimental data, but and it can be used to confirm experimental data. Again, we're given an elementary reaction and we're asked to write the rate law. So here we have two molecules of hydrogen iodide reacting to form hydrogen and iodine. And since we're told that it is an elementary reaction, we know we can use those coefficients to determine the exponents in our rate law. And so our rate law is rate equals K times the concentration of hydrogen iodide squared. Pretty simple and straightforward. We should be able to go the other direction as well. So if we're given a rate law, we should be able to write the balanced chemical equation from that rate law. From this rate law, knowing that we have an elementary reaction, we can see that we have 2 molecules of nitrogen monoxide reacting with 1 molecule of oxygen. And so we're going to write a reaction that's 2 molecules of nitrogen monoxide reacting with oxygen, and that's going to give us 2 molecules of nitrogen dioxide. You wouldn't be asked to write this because you're not expected to be able to predict that product, but you might be asked to choose this from a multiple choice question. Okay, so that's elementary reactions, pretty simple and straightforward. Let's talk about this idea of collision theory. So we have talked about all of these things that cause reactions to speed up or slow down, different factors that impact rate. And we're going to talk today about why that is. And so we know that as temperature increases, rate increases. We also know that that means that K, that coefficient in our rate law, is temperature dependent. The question becomes why? So we know that in a chemical reaction, bonds are broken and new bonds are formed, generally speaking. Molecules can only react if they collide with one another. But if you look at a reaction and you calculate the number of collisions, the rate of reaction is much lower than the number of collisions. And as always, the question is why? Well, there's really 2 factors that we need to take into consideration. And so we're going to talk about effective collisions. In order to have an effective collision, molecules have to collide with enough energy to break those bonds. And we know that bonds require energy to break. Then the formation of new bonds can release additional energy. But if that first collision doesn't occur with enough energy to break the bond, nothing's going to happen. Okay, so we can see here we have our molecule before the collision and we have an atom over here before the collision. They collide. This bond between this green atom and this blue atom is broken, and this collision has to have enough energy to break that bond. And now the new bond is formed, and that's going to release energy. That energy that's needed to break the bonds is what we call activation energy, and we abbreviate that with a capital E and a subscript A. You will also sometimes see it written as a capital A. Okay, so there's a minimum amount of energy that's required for a reaction, and we call that the activation energy. So just as our golfer here needs to hit the ball hard enough to get it up and over that little hill at the edge of the green, our reaction can't occur unless the molecules have enough energy to get over that activation energy barrier. So that's one piece, that's one factor of an effective collision. The collision has to occur with enough energy to overcome the activation energy barrier. But there's another piece as well. And that piece is orientation. So if this, in our collision here, if this green atom had crashed into this red end, then it's not in the proper orientation to form the new bond. And so that reaction won't happen. So they have to collide with enough energy and the right orientation. So 2 pieces to an effective collision: energy and orientation. So this means that our collision theory in general says that our rate is proportional to the frequency of effective collisions. Okay, so one thing that we're going to talk about in terms of being able to predict whether or not our molecules have enough energy. And this is why increasing temperature, because it increases the speed of the molecules, is going to increase the number of effective collisions, because it means that more of our collisions are going to have that energy. So we're going to go back to this idea of the Maxwell-Boltzmann distribution. We talked about these earlier in the year. The Maxwell-Boltzmann distribution is this graph that gives us the fraction of molecules on our y-axis and their kinetic energy or their temperature on the x-axis. And we remember that temperature is just a measurement of the average kinetic energy of the molecules in a sample. That doesn't mean that at a particular temperature, all the molecules are moving at the same speed. We know that there's a wide distribution of kinetic energies, but that the average is the temperature. As temperature increases, as this average moves farther over, our curve is going to flatten out and it's going to broaden out. So at a lower temperature, we have a narrower distribution. At a higher temperature, we have a broader distribution. If we think of this dotted line here as our activation energy, that's the minimum energy that's needed for the reaction. You can see that the fraction of molecules at the lower temperature is much smaller. Fraction of molecules that have that energy is much smaller than the fraction of molecules that have that energy at a higher temperature. So at higher temperatures, a larger population of the molecules has a higher energy. That means that more of the molecules, more of the collisions are going to be effective because more of your collisions are going to have enough energy to overcome that activation energy barrier. And so the reaction rate is going to increase. We can actually find that fraction of molecules using this equation. You are not ever going to have to use that equation, okay? But it is there. It does exist. There's a way to find it. And this becomes important because we then can find that as a derivation of that equation, we find that the natural log of K is directly proportional to 1 over temperature. Okay, again, bear with me, there's lots of math here. Okay, so here's our graph showing that natural log of K is directly proportional to 1 over T, and the slope of this line, the M, the slope of this line is equal to the negative or the opposite of activation energy divided by R, where R is that gas constant, the 8.314 joules. Okay, we can then derive this equation, which is called the Arrhenius equation. This comes from that line. This is the equation of that line. The natural log of K is equal to the negative slope times 1 over T plus the y-intercept. And then that derives back to this, where K, that's our constant, is equal to the frequency factor times E raised to the negative EA over RT. This is called the Arrhenius equation. Calculations with the Arrhenius equation are outside the scope and sequence of the AP Chem exam. But it's important that you guys recognize that the larger K is, the smaller the activation energy is, or the larger the activation energy, the smaller K is going to be. And that just comes back to logic, but it is also helpful to be able, for those of you who are math brain, to be able to relate it to this equation. So again, the larger the activation energy, the smaller the K, and the smaller the activation energy, the larger the K. This means that reactions with small activation energies go faster. Reactions with large activation energies go more slowly. Okay, and that covers it for our lesson today. So if you have any questions about collision theory or about elementary reactions, just let me know.